Hi, everyone, and welcome to today's Kubler online meetup. I'm Terry Shea, and we'll be discussing Kubernetes, data science, and machine learning today. We've seen a lot of interest in using Kubernetes for machine learning and data science workloads within the last few months, and the recent release of Apache 2.3 with native Kubernetes integration really highlights this trend. Today's presenters will be Vlad Penkin, Oleg Chunikin, and Arkady Urachetnoy. We started this series recently, and you can find previous meetups on our website and YouTube channel. Before we start, we wanted to highlight that this is a meetup and is supposed to be dynamic. So feel free to post questions in the chat during the presentation. We'll respond to everyone. If for some reason we are not able to read your questions out loud, we'll definitely be getting back to you after the meetup. There will be a demo at the end by Arkady. He'll be talking over a pre-recorded demo of machine learning, data science, and Kubernetes. And first, I want to tell you a little bit about Kubler. This presentation is really on the broader subject of Kubernetes with data science and machine learning, but we're sponsoring it, so we wanted to take a minute to tell you about our Kubernetes platform. Our platform enables IT operations staff to easily deploy, run, and manage Kubernetes clusters, and to do that on-premise or in multiple cloud environments. The slide you're looking at is sort of what we might call a architecture slide of Kubler, and it shows master and worker nodes running in different environments, and it highlights the security with the lock in the top one, the fact that you can set ingress and have persistent sessions in another viewpoint there, and then persistent volumes for storage. We build in logging and monitoring every time you set up a cluster so that you can go ahead and have monitoring of both your application and your infrastructure. And we also enable you to have storage and backup scheduling set throughout a centralized console. There is ability to download our Kubler demo, which we call Kubler in a box, on our website. So if you walk through this session with us today and are interested in playing around with Kubernetes and data science, one of the best ways to do that would be to download Kubler in a box and to give it a go. So Vlad, it's over to you now for the first part of the presentation.
Thank you, Terry. So I just wanted to make a short reminder or brief overview about machine learning in general and typical challenges and problems machine learning is trying to solve. And right now it's a very hot topic. So, and it is evolving very quickly. So, and common machine learning challenges or problems machine learning trying to solve are, as of now, computer vision, natural language processing, speech recognition, different kinds of prediction, anomaly detections, and so on. So, and if you are talking about science part for machine learning or data science, so there are different types of problems. So two most common are supervised learning. So, and here, so typical examples are classification problems. So, and classification is when you have a data and you are trying to label it, and you already know the result for training data set. It's like you have labeled a set of images with dogs and cats, and then you are training your machine learning model to say, is it a dog or is it a cat? So another example will be a regression problem. In a regression problem, so we are trying to predict not a label, but a quantity. So, and typical examples could be is to predict stock prices or house prices. So, and you need to train your machine learning model to predict a number, not a label. So another class of a problem is unsupervised learning. So, and for this, you have a data, but you don't know answer at the beginning, and you are trying to find a meaningful structure, or you are trying to analyze your data set and find similar data points, and at the beginning you don't know the answer, so you ask the machine to find it. So, and if you are talking about technology or process for machine learning, so I would say there are 5 main steps. So first one is you need to work with your data sources, and data sources could be database, file storage, and it could be batched input or it could be streams. So you need to work on data preparation. So you need to clean it and you need to transform it so machine learning model works. And depending on a machine learning algorithm, so you need to spend a lot of time on feature engineering or less, depending on the approach. Then you need to train your model and using data you have, and if, for example, this is a classification problem, so you already know the labels and you have your training data set. So you train the model, then you optimize it. And for model training and for model optimization, when we talk about the model optimization, we are talking about finding the best combination of model configurations or parameters, so you can get the best result in terms of accuracy. So in most cases, these tasks are quite compute intensive and does require a lot of computational power. And after you train your model, so you can use it in real life, for example. Usually it is called model serving or inferencing. So basically you have a trained model and it knows how to distinguish cats from dogs. So, and then here you are. So you can make a photo and, ask the model, is it a dog or a cat? And after that, or in parallel, so with steps number 2, 3, and 4, so we need to do a lot of analysis. So we need to do data exploration, results exploration, and so the new frontiers are tasks which are related to interpretations. So basically, you're trying to understand why is model thinking that this is a dog, a cat. So, and what are the key elements in the data, so which says this is a dog, a cat. So, and that concludes my overview for the machine learning, typical machine learning tasks and process. And I'm passing the work to Oleg, so he can talk about Kubler and Kubernetes and how it can help with solving typical machine learning challenges.
Hello, thank you, Vlad. So I'm going to talk about Kubernetes, as Vlad mentioned, and first of all, why Kubernetes is good for machine learning. First place, first of all, Kubernetes is a great orchestration framework, which seemingly is a winner in a container orchestration war of last year. It looks like it became a standard de facto for containerized load orchestration. Pretty much every vendor out there incorporates Kubernetes in one form or another into their solutions. And so what makes it great solution for general purpose containerized loads also makes it good for machine learning loads. So support for scalability and high availability out of the box, very pluggable and extensible architecture, great separation and very convenient separation of concerns for between development teams, operations teams, and infrastructure management teams. Each of them may use Kubernetes to so largely without intersecting their responsibilities. It's cloud and operating system agnostic, has a number of functions for operational concerns like RBAC, limits, quotas, etc. and many other characteristics. So having said that, I'm going to concentrate for the next few slides on features that make it especially good for machine learning and data science tasks. And so the first of it is, of course, what is the core of Kubernetes functionality. It's scheduling functionality. So Kubernetes architecture is based on master, which tracks target state of the system, and a number of controllers, each of which is responsible for certain aspects of system functionality. So some of the controllers are responsible for running specific containers on specific nodes, other, and this is, by the way, called Kubler, Kubernetes agent running on each and every node. Other controllers are responsible for making a decision on which node a certain container should run, which is called scheduler. So, and flexibility of those controllers and their configurability, and especially scheduler, makes it very useful in machine learning, for machine learning tasks and data science tasks. So it supports both static rules for scheduling containers on different nodes, as well as extending scheduling algorithms with runtime plugins. Static rules include things like definition of affinity and anti-affinity for both containers to nodes and intercontainer affinity and anti-affinity. It may be specified as both mandatory rules or weighted preferred rules. So this not only allows you to very flexibly and without too much of reference to your specific infrastructure defined topology of your application, but also make this definition adjustable in situations where your infrastructure changes. And this is a case we see more and more often nowadays, especially when you have an auto-scaling enabled, or when you decide to use a hybrid environment with burst expansion into cloud, or when you work with multiple clouds, trying to reduce resources costs, because as we all know, prices may vary significantly in different clouds for different types of resources, etc., etc. Next feature I would like to talk about is operational capabilities of Kubernetes. And here, while Kubernetes is a great operations abstraction layer for applications running on top of that, Kubernetes also provides a number of very flexible SPIs, service provider interfaces, that enable building convenient operational frameworks for Kubernetes itself. So, and we see vendors developing those frameworks. Kubler is one of those vendors. So usually what operations for Kubernetes gives you is, well, ability to set up Kubernetes clusters in secure and reliable fashion without going into depth of Kubernetes configuration. Support for hybrid environments and multi-cloud environments, centralized log collection and monitoring, identity management, audit, infrastructure management, managing image repositories, backup and disaster recovery. So all those operational concerns are sort of passed over to your applications running on top of Kubernetes essentially for free. So you have them out of the box without a need to do that for each and every application you run. So next feature I'd like to talk about is auto-scaling and scalability. So, and in case of Kubernetes, again, it provides a very convenient way of implementing it for practically any application running on top of Kubernetes. So two components of scaling architecture of Kubernetes are, first of all, horizontal pod autoscaler. It's a Kubernetes concept, Kubernetes controller, or control object actually, which can be configured in such a way that your application is scaled up and down based on various metrics, and those metrics may be standard like CPU load, or you can use custom metrics. So Kubernetes, based on your configuration, will automatically increase or reduce number of containers your application runs. The second part of the equation here is actually scaling infrastructure, because you can scale containers as much as you want, but if there is not enough infrastructure resources to run them, so they'll just stay unscheduled. So Kubernetes cluster autoscaler is a component which watches how many resources is required for your containers running inside Kubernetes, and if resources are not enough, it starts adding new hardware to your cluster. If it sees that resources are underutilized based on your rules, it starts scaling your cluster down. And again, this is very flexible framework which you configure according to your needs and infrastructure. Supports different policies, scheduling rules, cooldown periods, multiple node groups, clouds, etc., etc. And I already talked about operations. So, and Kubernetes extends convenience of iterations and various iterations considerations to your applications running on top of it. And Kubernetes community came up with this idea of operator, or a component which knows how to manage your application and simplify that for you. And there are a number of operators already developed for multiple software components, especially ones frequently used in data science and machine learning as well. So what operators give you is ability to simplify and reduce effort needed to maintain any piece of software comprising your application stack. So some of those pieces of software that you may want to run as a part of your stack include, for example, HDFS and Hadoop. So operators exist for those components. You know that both HDFS and Hadoop have their own operational solutions, but convenience of running them on top of Kubernetes, well, maybe clear. So you unify your operation layer. You don't have to manage it separately. So you run it together with other applications in the same similar manner. So another data storage solution that becomes more and more popular in this area is Rook and Ceph. So while HDFS grew sort of on top of Hadoop, so Rook and Ceph come from distributed file storage systems world, but again, with development of scaling feature and operational features for CF, it became more popular for data science load as well. And Roop is essentially a Kubernetes operator for general purpose CF distributed file system framework. Next item on my list is support for GPU and special compute devices. So Kubernetes does support them on several levels. So Kubernetes considers such devices as custom resources in addition to standard resources like CPU, RAM, storage that may be available on each node. Kubernetes allows definition of custom resources, and GPU, FPGA are essentially such custom resources for that. NVIDIA supports integration with Kubernetes. So NVIDIA provides both plugin for Kubernetes, which allows publishing NVIDIA GPUs as custom resources for Kubernetes. NVIDIA also develops a Docker runtime plugin, a specialized Docker runtime plugin that simplifies using NVIDIA devices in containerized load. So this requires some assembly because you need at least 3 components in your Kubernetes cluster set up correctly when you want to use GPUs. It's GPU drivers installation with NVIDIA container runtime setup and then NVIDIA device plugin setup. But again, Kubernetes operations framework, Kubler in particular, simplify this coordinated setup for you. Okay, this concludes overview of Kubernetes machine learning and data science specific features. So Arkady, the table is yours.
Okay, thanks Oleg. Today I'm going to introduce you to the major stacks which can help you solve your machine learning tasks. And I'd like to show you a couple of frameworks which can help us out with this. Some of these frameworks are pretty new, so let's do a brief intro to some of them. First one I want to talk about is TensorFlow Operator. It's a CoopFlow project, and it's a rather new framework which can help you automate some of the operations with TensorFlow. Another one I want to mention is also quite new. It's called Spark 2.3. 2.3 is the newer version, and this newer version has a lot of differences between the old version 1.x of Spark. This new version is fully compatible with Kubernetes, and we'll go over some details shortly. Now, a lot of companies use their own in-house solutions as well, because if you're using Kubernetes to run your machine learning tasks, you can just create your own Docker container, package up your code that has your algorithms and calculations, and then you can use your cloud or on-premise Kubernetes instance to calculate and distribute your workloads. Another new solution I want to mention is Apache Beam, which is not exactly a full stack, it's more of a model for machine learning. And using Apache Beam, we can hook up different runtimes, for instance, Spark, to calculate our workloads. There are also quite a few open source solutions that are coming from different vendors. And of course, every big vendor in the cloud, and not only in the cloud, on-premise as well, they have their own frameworks for these machine tasks. Generally speaking, we have a lot of options how we can solve these tasks, either with Kubernetes or without Kubernetes. Let's briefly talk about CoopFlow. CoopFlow is an operator for TensorFlow. It's designed to simplify scaling and deploying machine learning applications. However, the current implementation only supports TensorFlow, so keep that in mind. So let's briefly chat about Spark too. Spark is a well-known framework for solving machine learning tasks, and there are 2 versions of Spark out there, an old version and a newer version. The previous version of Spark, version 1.5, was designed in a previous era before Kubernetes. So as a result, it consists of a bunch of master and workers, and the old version of Spark has a static design, so it requires you to have your own static Spark cluster. Of course, you can still delete and add your own nodes, but it's not as straightforward as we can do it now with Kubernetes, and it requires additional steps. After version 1.5, the Spark community released a new version of Spark with native Kubernetes support, which has the new design. The new design of Spark consists of two components. The first component is a driver, which is like a master. It has the ability to distribute tasks between workers and then collect information. Now for scheduling, and that's scheduling workloads and Kubernetes clusters, the new version of Spark uses the Kubernetes scheduler as well as Kubernetes components, and it's going to delete new pods and create new pods automatically. We're also able to use new abilities of Kubernetes, for example, horizontal pod scaling or cluster auto-scaling, and this is so we can dynamically add and delete executors. So the new Spark design will help make a more flexible Kubernetes solution while still allowing you to use your old code base as well as old libraries. So I think it's a great step for the future for Spark-based solutions. All right, so the next available solution is an in-house built solution. So that means we can create our own Docker containers with some machine learning code. It could be a GPU-based machine learning task or a CPU-based learning task. So it could be classical machine learning tasks or a neural network task. And we can use Kubernetes as a scheduler for this Docker container. We can even add Prometheus and Grafana on top of that for monitoring, and that's to monitor our workloads and increase and decrease our nodes and to help with other tasks also. And of course, one of the most important parts is a custom implementation of distributed task scheduler. You could use some framework like Celery, for example, or another framework here. So this part of the stack is responsible for generating and creating tasks for Docker images and collecting information. Now I want to show you a short demo. It's a demo that illustrates a lot of Kubernetes abilities, and I can show you how these work. So generally we have our image, which contains the machine learning algorithm. And the idea behind this demo is that we have many copies of one algorithm running, but we can run many tasks with different hyperparameters, and then we can pick out the best value during our calculation. We also utilize RabbitMQ, which we use to distribute tasks between different workers, and we also use it to collect all our results. And one of the most interesting uses of RabbitMQ here is to collect metrics so that we can make decisions about whether we want to increase the number of workers or decrease the number of workers. So our workload is not fixed, and it depends on how many messages we have in the queue in the RabbitMQ. All right, let's take a look at the demo. So I created a Kubernetes cluster using Kubler, which is probably the simplest step of this demo. And here we're using the latest version of Kubernetes, which is at this time 1.10. I created one master configuration with 5 nodes. Here from the Kubler user interface, we can open the Kubernetes dashboard. And as you can see, in our current cluster, we only have one worker, which shows our Docker container, which is running our render forest logic. We also have RabbitMQ, which is deployed in this Kubernetes cluster. And we use Prometheus and Grafana. As you can see down here, we can monitor the number of workers and the number of messages in queue. So the next step is to run our workload. And that means that our master is going to generate about 20,000 messages, where every single message is work for our Docker container. And once I kick that off, let's go ahead to our dashboard and take a look. Here, as you can see, we have 20,000 messages in our queue. Here, our workers are starting to get information from the queue, and they're starting to work with their tasks. HPA has recognized that we have a bunch of messages in our queue, and it automatically scaled up our pods. So I just want to show you how our current horizontal autoscaler is configured. And yes, we have about 20,000 messages in our queue, and in our configuration, the autoscaler starts scaling up when it sees more than 5,000 messages. So the 5,000 is the threshold here. After that, the number of pods will increase. And here we're setting the limit to 20,000, but of course it can be any other number, even higher than that, and that depends on your application. So now, if we wait for some time, the Kubernetes pod autoscaler will automatically increase the number of pods, but since this video is pre-recorded, I'm just going to show you quickly what happens at every step of the way as the pods are being increased. So here's an example of the pods being doubled And now instead of 4 pods, we have 8 pods. So here Kubernetes is still increasing the number of workers for us. All right, let's keep going. Okay, so now we have 16 pods processing, and this just gives you an idea that you can have as many as you want. And that'll allow you to work with your workload as fast as you can. And finally, after all the processing, I just want to show you what happens with Kubernetes if I purge the queue. This will demonstrate that the Kubernetes horizontal pod autoscaler will recognize that there are 0 messages in the queue, which will in turn make the Kubernetes horizontal pod autoscaler automatically scale down our application. Usually this process takes a few minutes, but we can change some parameters to speed this up a bit. And here now you can see that Kubernetes has decreased the number of workers from 16 to 1. So that's it for the demo. Back to you, Terry.
Okay, thank you, Arkady. There were a few questions in the question tab, and so I just wanted to go through those with you guys. And maybe Oleg Chunikin, you might want to take this one. And the question is that they've heard that data science processing times improve dramatically when using GPUs. Can you give me an idea of how much faster they are and what kind of processes can take advantage of GPUs?
Yeah, sure. Well, one example, we just recently tested a new framework called H2O, a convenient tool to do data science work on, and it supports both CPU processing and GPU processing. So we saw 15 times increase in speed of processing. So I'm sorry, there's essentially, instead of 10 hours processing on CPU, we got 40 minutes time on GPUs.
Oh, that's great. So from 10 hours down to 40 minutes is an impressive difference. So Kubernetes' ability to support GPUs now as a resource seems like it would be very helpful for certain types of data science. But I think the other part of the question, Oleg, was, I've heard that it's for parallel tasks. Can you comment on what kind of processes can take advantage of GPUs at all?
There are certain sets of tasks that are better for GPU load, especially ones that allow massive parallelization. Actually, I think Vlad may have a better categorization here. So
great, Vlad.
So Oleg is absolutely right. So there are some machine learning loads which could be highly parallelized, and classical example is CNN, convolutional neural nets, which are used for image recognition, and you can speed it up significantly using GPU. But on the other hand, depending on a machine learning model and algorithm, sometimes GPUs cannot help you. So, and the classical example is when you're dealing with time series and try to use RNN or LSTM neural nets. So GPU cannot help you. Maybe FPGA, or in general, so you need to stick with CPU.
Thank you, Vlad. I don't know which one of you wants to take the next question, but we had mentioned Apache Spark 2.3 a couple of times, and its native integration to Kubernetes. Why is that such a big deal, or is it? Is the question.
Yeah, I can start, and Vlad, you chime in if you want to add something. Apache Spark is a very well-known and commonly used framework, so it's very important to keep this knowledge base and expertise. So people who are used to work with Apache Spark continue working with Apache Spark. So nothing changes for data science team, and at the same time, your operations team can benefit from Kubernetes capabilities and provide a higher level of service to both data scientists and developers. So what's so important about this recent change in Spark and supporting dynamic clusters and dynamic load allocation on Kubernetes? Well, it's exactly that. So instead of using Spark-specific features for scheduling and expanding autoscaling and integrating it in some custom way with Kubernetes capabilities, you can just again offload this task of managing your resources, both infrastructure and container, to Kubernetes, where they are already being solved by in a more generic manner, so to say.
Thank you, Oleg. And then the third question we had relates to IoT, and it says that they believe that IoT will require stream processing of data and machine learning, or at least analytics at the edge. Do you think Kubernetes is a good fit for this use case?
Well, certainly in several aspects. So first of all, again, it's scalability and availability and ability to handle very dynamic and dynamically changing load helps a lot with IoT. So you get incoming stream of events. This stream may vary depending on multiple factors, and Kubernetes could scale your processing capacity according to these variations quickly enough. But
we seem to have lost Oleg there. We'll give him a second to see if we can get him back.
It looks like we had some technical difficulties here. So, but yeah, I'll continue. Another aspect of why Kubernetes may be good for IoT loads is because Kubernetes can help with managing your applications on the edge. So you can use the same framework for scaling, for operating your containers or applications on the edge machines using the same Kubernetes. It's a popular and quickly developing directions now.
Well, thank you, Oleg. I think the idea of automation with the amount of data that is going to be streaming in through IoT and the relationship between machine learning at the edge and Kubernetes seems like it's similar to what we showed today, but will have its own different use case requirements. So appreciate that. So that concludes our session for today. We'd like to thank everyone for joining today's online meetup. We'll be uploading this to our website. Feel free to reach out with questions or suggestions of topics or other feedback. And the best email address for that would be contact@Kubler, KUBLR.com. Our next online meetup topic will be application deployments with Kubernetes. Stay tuned as we announce a date for that shortly. We hope you can join us again.